to prove that a function f from x to y is injective, so you may show either that f of x1 equal to f of x2 implies an x1 equal to x2, and this is how we wrote the definition. But also you can prove the contrapositive. So remember, if this statement here, let's say, is P, and let's call this Q, so we're essentially saying prove P implies Q, and we know that this is equivalent to not Q implies not P, right? So this is the contrapositive. And so that means that we could either prove this, so if f of x1 is equal to x2, then x1 is equal to x2, or the contrapositive, so not Q is x1 different than x2, implies in not P, which is f of x1 different than x2. So we can also show that if x1 and x2 are different, then their values have to be different when they go through the function. So different inputs give different outputs, right? Okay, so the usual approach, or like we said, the direct approach might be just to prove the top one. How can that work? Suppose f of x1 is equal to x2 for arbitrary x1 and x2. So this needs to be true for every x1 and x2. That's why you need to take arbitrary. And then you use algebra or logic reasoning to show that x1 is equal to x2. And once this is shown, you can conclude that f is injective. So let's take a look at an example of this. So suppose we want to show that this function here, from the real numbers to the real numbers, defined by f of x equal to 2x plus 1 is injective. So first let me state that if you were to plot this function, it would look something, so this is a line, and when x is equal to 0, it passes at 1. And so it's going to be, and it has the slope 2 here. So it's going to be some line like this, let's say. And the idea is that every input here, so the x-axis, so this is your x, and this is your f of x. Notice how if you have different inputs, let's put different colors here. If you have different inputs, their values, their outputs, f of x, are going to be different also. You're not going to get, these two are not the same. So if these are different, then these are different, right? And intuitively, it seems like it's true for this function. And let's see how we can prove that. So we will do a direct proof. So proof. So again, suppose that f of x1 is equal to f of x2 for some arbitrary x1 and x2 in the real numbers. Okay, so what does this mean? Then we have that 2x1 plus 1, so that's the value of f of x1, is equal to f of x2, which is 2x2 plus 1. Okay, so now if we subtract, so subtracting 1 from both sides, we obtain that 2x1 is equal to 2x2, and then dividing by 2 on both sides, so dividing by 2, we obtain x1 equal to x2, which is what we wanted to show. So since we started assuming that f of x1 is equal to f of x2 and concluded x1 equal to x2, it follows by definition that f is injective. Okay, and this concludes our proof. So let's take a look at it again. So let's recap here. So we want to show that this function here is injective, and we're doing a direct proof. So what do? We need to assume that f of x1 is equal to f of x2 for arbitrary x1 and x2. Okay, and then we need to conclude that this will happen, that x1 is equal to x2. In this case, how would it happen? Well, once you write this out, you will get this equation, and then you just do algebra on this equation here, and you will conclude that x1 is equal to x2. And so since we showed that f of x1 equal to f of x2 implies an x1 equal to x2 for every x1 and x2, that means by definition that this function is injective. Okay, let's look at a non-injective function. So now we can do the same as we did before. For intuition, we can graph the function. So here we want to look at this function from the reals to the reals, f of x equal to x squared. So this is a parabola. Let me draw it here. So this is going to be like some parabola here. And the idea is that now we want to show that it is the case that we can have 2 points that have the same output. So if we look at the parabola here, you can see that if I were to search, so if I were to like take a point here, oh, let me write it out. I can try to take a point here, and it'll identify. So the idea with this point in the output is that it's showing me that there are 2 points in the input that lead to it. So as an example, if I were to take this point to be 1 here, then 1 squared and minus 1 squared would be equal to 1. And that can't happen, right? So we have the same, different inputs giving the same output. So let's write that down. So let's write a proof that this is not injective. Okay. So in this case, it's a proof by counterexample, sort of, right? We just need to find one place where injectivity fails. And so consider the distinct elements, x1 equal to 1 and x2 equal to minus 1. Then f of x1 is going to be equal to f of 1, which will be 1 squared equal to 1. And this will be equal to minus 1 squared equal to f of minus 1 equal to f of x2. So since we have 2 distinct inputs, x1 different than x2, that produce the same output, f of x1 equal to f of x2 equal to 1, so equal to 1, it follows that f is not injective. So to show that the function is not injective, one way is you just need to show that there exist 2 distinct points, in this case 1 and minus 1, that have the same output, in this case 1.